This lecture will cover the principle of Routh Hurwitz stability criterion. This is a mathematical test that is a necessary and sufficient condition for the stability of a linear control system. As we saw in lecture 5, a sufficient condition for stability is that the real part of the poles must be negative numbers, which means that the poles are always located on the left side of the S-plane. When a transfer function is given as a function of the location of the poles, such as this one, it is easy to see that all poles are negative numbers and thus this system is stable. However, the task becomes a lot more complicated when the transfer function is given as a polynomial such as this one. Finding the roots of this polynomial is not necessarily a trivial task, especially when the coefficients of this polynomial are functions of the variables that represent the control gain. This is the objective of the Routh Hurwitz stability criterion. It's a mathematical tool that will help assess the stability of a system without having to calculate all the poles of the transfer function. By the end of this lecture, you should be able to understand the principle of stability, define the conditions required for stability, as we saw in lecture 5, and apply the Routh Hurwitz stability criterion to a given system. Before we talk about stability, it is important to define what stability means. Are these control systems stable without feedback control? The answer is no. None of the systems are stable. A bicycle without feedback control simply falls and cannot maintain equilibrium. The rider will make small adjustments based on the deviation from the horizontal line, and that is what makes the bicycle stable. A Segway operates in the same way. The only difference is that these adjustments are made electronically. The orientation of the Segway with respect to the desired line can be measured and now sent to a feedback control, where the desired position in this case is 0 degrees. Any deviation from 0 degree will create an error, and the feedback control will make adjustments to eliminate that error. These are good examples of naturally unstable systems that can be stabilized using feedback control. In the same way, we can stabilize unstable systems. We can make stable systems unstable if you don't design the controller properly. This is a good example of destabilizing positive feedback. Here the microphone picks up sounds from the voice and amplifies those sounds through the speakers. In theory, this proportional gain that amplifies the sound magnitude could be very large. However, past a given gain, the microphone will start to pick up sound from the speakers. And this sound coming from the speakers will now go through the loop and will be amplified further and further. This infinite loop will keep amplifying the signal until the system reaches saturation or until something breaks. In control systems, we would call that a positive feedback loop. This is a good example of a stable system that can be made unstable if the controller is not designed properly. The objective is to increase the gain to the maximum such that you can amplify the voice as much as we can while maintaining stability. So there is a maximum gain that will lead to instability, and that maximum gain needs to be determined. Here is another example. It's a very simple and perhaps inaccurate example of a stable system that can be made unstable with a high control gain. In this example, an individual is taking a shower and wants to control manually the temperature of the water. The desired temperature is compared with the water temperature, and adjustments in the valve position are made to regulate the temperature. The controller here is simply the human. If the water temperature is below the desired temperature, that will create an error that is greater than 0. If the error is greater than 0, then the valve will be turned to hot. This amount, this proportionality constant between the error and how much the valve is turned, is the control gain K. If now the water temperature is above the desired temperature, that creates a negative error, and thus the controller or the human determines that the valve is to be turned now to cold. There is a delay between the action and the actual change in the water temperature. This delay can make the system unstable if that gain K is too high. So let's assume that this delay exists and that the human here is impatient. This control gain is very large. If the control gain is very large, and let's assume that initially the water temperature is below the desired temperature, the positive error times a very large constant will result in the valve being turned all the way to hot. When the valve is turned all the way to hot, now the water temperature will start to rise. And when it exceeds the desired temperature, that will create a negative error. That a very small negative error multiplied by a very large control gain will now result in the valve being turned all the way to cold. Once the valve is now in the cold position, the water temperature will decrease slowly. And again, when now the water temperature is below the desired temperature, the valve will go all the way to the hot position. And this continues back and forth, and the system never reaches equilibrium. The concept of stability can be classified into 3 main states. A stable system is a dynamic system with a bounded response to a bounded input. This is shown in this first representation. In a stable system, if a bounded input is given to it, the system will oscillate before it settles back at a given position. It will always reach a stable position. In a neutral system, when a bounded input is given to it, the system will start to oscillate and will never stop. That is called a neutral system or a marginally stable system. And an unstable system may be in the equilibrium position, but as soon as an input is given to it, the system will become unstable and you have an unbounded response to a bounded input. In mathematical terms, a system is stable if all closed-loop transfer function poles lie in the left half of the S-plane. As we covered in Lecture 5, this comes from the fact that the real part of the poles will create exponentials, and when the poles lie on the left side of the S-plane, those exponentials decay to zero. If the poles lie on the right side of the S-plane, the exponential tends to infinity. Even if the function has several stable poles, all it takes is one pole to be placed on the right side of the S-plane to make the entire system unstable. Let's define the concept of stability more formally. Consider the generic transfer function given in equation 1. This is simply a combination of real zeros multiplied together, real poles, and complex conjugate poles. For an impulse input, the output response when n equals to 0, that is, this 0 at the origin doesn't exist, is given in equation 2. We see here a combination of exponential and sinusoidal responses. All the exponentials are functions of sigma and alpha. This will come from the real part of the pole. So long as sigma and alpha are positive, that is, the poles are located on the left side of the S-plane, both of these exponentials will eventually tend to 0. And the system will have a bounded output for a bounded input. However, if sigma and alpha, at least one of them, are negative numbers, then these exponentials will now tend to infinity. Thus, a necessary and sufficient condition for a feedback system to be stable is that all the poles of the system must have negative real parts. That is, they lie on the left side of the S-plane. This is covered in more details in Lecture 5. Now we can link the concept of stability and the location of the poles. A stable system will have all poles on the left half plane. A neutral system or marginally stable will have poles that are purely imaginary, that is, they are placed on the imaginary axis. It doesn't matter how many poles the transfer function has, if at least a pair of poles is placed on the imaginary axis, that is sufficient to make the system oscillate indefinitely and make it marginally stable. Same goes for an unstable system. Regardless of the number of poles, if at least one pole is placed on the right side of the S-plane, the entire system is unstable. Let's touch a bit more on the concept of marginally stable. This happens with some poles of the closed-loop transfer function are purely imaginary. Consider the transfer function given in equation 3, 1 over s plus 10 times s squared plus 16. We have 3 poles, one at negative 10, and 2 at plus minus 4j. The real pole at negative 10 will create an exponential that decays to 0. The purely imaginary poles will create a sinusoidal waveform without any exponential because the real part is 0. The total response of the system is the combination of these two, which will result in something like this. We see the exponential function decreasing to a constant value or to 0, and you are left with the oscillations caused by the complex poles. For this particular function, this is the time response will oscillate indefinitely, because at least one pair of poles is placed on the imaginary axis despite the fact that the function has other stable poles. The Routh Hurwitz stability criterion is a necessary and sufficient condition for stability. It's simply a mathematical way to determine the location of the poles and to assess the stability of the system without actually having to solve for the poles. This is very handy for systems that have high orders or for those where the coefficients of the transfer function are functions of control gains that are to be determined. This can be a bit intimidating at first glance, but we'll break this down into small pieces and you'll see it's relatively simple. The Routh Hurwitz stability criterion will always take the characteristic equation of the transfer function. If you have a transfer function in this form, the characteristic equation is the denominator of this transfer function, Q of s. The objective of the Routh Hurwitz stability criterion is to take Q of S, put that in a special array, and do some mathematical operations. And this special array is made in a way that to determine the stability of the system, all we have to do is to look at the signs of the first column. The number of roots with positive real parts in the characteristic equation is equivalent to the number of sign changes in the first column. Now in the next slides we'll see how to fill out this array. For what follows, we are considering the array described in equation 4. It's simply a polynomial whose highest power is n and whose coefficients go from an, the highest power of s, to a0. The first step is to create the first column in the Routh Hurwitz array, and this is very simple. We are going to list the powers of s from the highest to the lowest power. If you're dealing with a fourth order system, we'll have s to the power of 4, s to the power of 3, 2, 1, and 0. The second step is to populate the first two rows of the array. The first two rows will now take the coefficients of this polynomial. We are going to start with the first element here being the highest coefficient of s. The second coefficient goes here, the third coefficient goes there, fourth, fifth, and so on. So we are completing this array in a up and down pattern like this. Let's consider an example: s to the power of 4 plus 5s to the power of 3 plus 2s squared plus s plus 9. This is a fourth order polynomial, so we can start the array with s to the power of 4 and go all the way to the s to the power of 0. And you can now populate the two rows in this array. The first element is the coefficient of s to the power of 4, that is 1. The second that goes here is s to the power of 3. S to the power of 2 is 2, s to the power of 1 is 1, and s to the power of 0 is 9. And you can now complete the array with a 0 here. Now note, if one of the powers of s is missing, say s to the power of 0 is not present, and we would have simply s plus 9, we still need to add s to the power of 1 to the array. In this case, the coefficient of s to the power of 1 is 0. So we would have 1, 5, 2, 0, 9, and 0. S to the power of 1 still exists, but its coefficient is 0, so typically we don't write it, but it needs to make it to the array. So here we have the two steps. Fill out the first column with the coefficients of s from the highest order to s to the power of 0, and complete the first two rows in this up and down pattern. The next step is to fill out the remaining rows. Let's start with the third one. Here is the formal mathematical way to do it, but as we start to do it, we'll see that there will be a pattern that will make things a lot easier. Let's look at the first element, bn-1, which is given here. bn-1 is given as -1 over the element just above it times the determinant of the four elements above it. So bn-1 would be an times an-3 minus an-2 times an-1 divided by -an-1. This is the mathematical way to do it, but you'll see the pattern here. When you're dealing with this element, we will have the top four elements be multiplied in this sort of loop. This element times that one minus the multiplication of this two divided by the negative of the element just above it. If we now go to bn-3, that is this cell here, we're going to use the same pattern, but now we're going to stretch the determinant by one column. And this would be the pattern between an and an-5 minus an-4 times an-1 divided again by the negative of where this loop starts at an-1. This is given. And now the process can continue to the fourth row. We are now dealing with c. cn-1 will take these four elements and will be divided by bn-1. So this would be an-1 times bn-3 minus an-3 times bn-1 divided by -bn-1. Moving on to cn-3, we now take this 2 and this 2 elements. So this first, the same operation, but it's now stretched by one column. And it would take the multiplication of this 2 minus the multiplication of those two divided by bn-1. And the process can continue until the array is completely filled. This is indeed a bit intimidating, so let's look at a numerical example that will make things a lot more clear. The characteristic equation of the transfer function that we are dealing is given here. It's a fifth order polynomial. In step 1, we need to prepare the coefficients of s in the most left column. We have the coefficient, the highest coefficient f to the power of 5 all the way to s to the power of 0. The second step consists in populating the first two rows in that up and down pattern, starting with the coefficient of s to the power of 5, that is 1, s to the power of 4, 2, here it is, 1 for s to the power of 3, 4, 11, and 10. If you did this properly, then you should notice that here we have the coefficients of every other power of s, and in the second row we should have the remaining coefficients. Again, remember that this pattern goes up and down like that. And now we can populate the other cells in this matrix. Let's start with the element here. The element here will take this multiplication divided by the negative of this number. This is the pattern we identified in the previous slide. Let's call this element A. A will be 1 times 4 minus 1 times 2 divided by negative 2, which is negative 1. We can now look at B. B will now be the cross multiplication of these 4 elements and be divided again by where it ends, negative 2. B is 1 times 10 minus 11 times 2 divided by negative 2. The next element here would now take the first column with the next one that I have to expand, and this is 0, 0. So obviously the result here is simply 0. Now that the third row is completed, we can move to the one with s to the power of 2. Starting with this cell, let's call that C. C is 2 times 6 minus 4 times negative 1 divided by negative 1. Or again, the same pattern that he had before. And this gives 16. Now this element here, let's call that D. D will take the same starting cells, but I now have to expand the determinant by one column. This will be 2 times 0 minus 10 times negative 1 divided by where it ends, negative 1, which is equal to 10. The next element here would need to take the expanded column, which has 0, 0. So 2 times 0 minus 0 times minus 1 divided by minus 1 is 0. This element here is simply 0. Now that the fourth row is completed, let's move to the fifth one, starting with this element. Let's call this element E, and E, you guessed, will now take this 4. E equals to negative 1 times 10 minus 6 times 16 divided by negative 16, and this is equal to 6.625. We can now move on here. So this will now take this 4, and because we have all zeros on this side, we have negative 1 times 0 minus 0 times 16 divided by negative 16. This value here is 0, and so is the next one. The last element that we can call F is obtained with these 4 elements divided by the negative of this one. So 16 times 0 minus 10 times 6.625 divided by negative 6.625. And this is equal to 10. Now that the Routh array is completed, we can assess the stability of the system by looking at the number of sign changes in the first column. Here is the first column. How many sign changes are there? From 1 to 2, no sign change, positive numbers. From 2 to negative 1, 1 sign change. From positive to negative. From negative 1 to 16, another sign change, negative to positive. 16 to 6.6, no sign change. 6.6 to 10, no sign change. Here we have 2 sign changes in the first column. This means that this characteristic equation has 2 unstable roots. The transfer function has 2 poles placed on the right side of the S-plane, and the system is unstable. Let's do another example. In this example, we again have a 5th order polynomial given here. Let's start by creating the Routh array. We start with s to the power of 5, the highest coefficient, and go all the way to s to the power of 0. Once that is done, we can populate the first 2 rows with the coefficients of that polynomial. Starting with the coefficient of s to the power of 5, that is 3, s to the power of 4, 1, s to the power of 3, 2, s to the power of 2, 1, s to the power of 1, 0, here it is. It's not shown, but it's here, 0 times s to the power of 1, and this needs to make it to the array. And finally, s to the power of 0, 1. So again, here we are using the up and down pattern. Now let's complete the remainder of this array. Starting with this value, a. For that value, we'll take these 4 cells and you'll divide that by -1. The determinant here is 3 times 1 minus 2 times 1 divided by -1. So the pattern is here, a equals to 3 times 1 minus 2 times 1 divided by -1. And this is equal to -1. If you now go to this cell, we have this pattern, 3 times 1 minus 0 times 1 divided by -1, which is -3. And the next element is clearly 0. Now let's go to this cell. The pattern we need is there. 1 times -3 minus 1 times -1 divided by -1. And this is -2. Moving on to this cell, now we have to stretch that pattern by 1 column. And this will be 1 times 0 minus 1 times -1 divided by -1, which is +1. The next cell is 0. And we can now move down to this. Here we have the pattern, -1 times 1 minus 3 times -2 minus -3 times -2 divided by -2. Very careful with the signs. And this is equal to -3.5. The second cell will be 0, the next one will also be 0. And the last one here, we have -2 times 0 minus 1 times -3.5 divided by -3.5. This is equal to 1. Now that the array is completed, is the system stable or unstable? The stability criterion states that the number of unstable roots is equal to the number of sign changes in the first column. Here we have the first column. How many sign changes are there? 0, 1, 1, 1, 2. 2 sign changes. The system has 2 unstable poles. These 2 unstable poles are placed on the right side of the S-plane. After some practice, we'll see that these patterns are very intuitive and the array is very easy to use. However, there are some special cases that we need to consider. But as a summary, we can say that stability requires all roots of the characteristic equation to have positive real parts. Count the sign changes in the first column, and that is the number of roots in the right half plane. Any sign changes indicates an unstable root. Let's now consider these special cases. In case 1, all elements in the first column are non-zero. For example, this one. If A2 is greater than 0, then the system is said to be stable if A1 is greater than 0 and A0 is greater than 0, so that there are no sign changes in the first column. If A2 is smaller than 0, then the stability will require A1 to be smaller than 0 and A0 to be smaller than 0. And this will also ensure that there are no sign changes in the first column and the system is said to be stable. This is the simplest case where all elements in the first column are non-zero numbers. One special case occurs when there is a 0 in the first column and the other elements in the row containing the 0 are non-zero. If you take this polynomial and fill out the array, you will see that at this location here we'll have a 0 element. This 0 will create problems because when you try to calculate C1, C1 will be 2 times 6 minus 4 times 0 divided by 0, and this blows to infinity. This always occurs when you have a 0 element followed by at least one non-zero element in the first row. The solution to this is very simple. When you get a 0 here, followed by at least one element that is non-zero, write epsilon instead of 0, and continue all the calculations as a function of epsilon. So here 1 times 4 minus 2 times 2 divided by -2 is 0. 0 would go here, replace that with epsilon. And now calculate the remaining elements as a function of epsilon. C1 is given here, D1 is given here. We see that are both functions of epsilon. Once the array is completed, now take the limit of everything that is a function of epsilon when epsilon tends to 0. The first one is C1. In C1, when epsilon tends to 0 from the positive side, this tends to 0, and the remaining here tends to negative infinity. The other element that is a function of epsilon is D1. Now let's take the limit when epsilon tends to 0 of D1. We know that a C1 tends to negative infinity when epsilon tends to 0. This here tends to 0. So the result here is a positive infinite number. Negative infinity divided by negative infinity. And now we can evaluate the sign changes. When epsilon tends to 0, we'll see one sign change here from a small positive number to negative, and a negative to a positive number from C1 to D1. So this system will have two unstable roots as well. The next two cases are separate in the textbook, but I think they can be combined into one. Cases 3 and 4 will occur when there is a 0 in the first column and the other elements of the row containing the 0 are also 0. For example, this case here. This happens in three cases. The first one is when you have two poles, one is positive and one is negative, and they are at the same distance with respect to the imaginary axis. The second case occurs when poles are placed on the imaginary axis. And the third case occurs when you have two pairs of complex conjugate numbers that are mirrored with respect to the imaginary axis. That is, they are placed at the same distance from the imaginary axis. Most often, this is the case that we will encounter. When you have an entire row of zeros, we may assume that this represents a transfer function with the poles that are purely imaginary numbers. This will occur here when k equals to 8. When k equals to 8, we have an entire row of zeros. And you can now say that the characteristic equation has purely imaginary roots lying on the imaginary axis like that. This will be very useful in the upcoming lectures to determine the maximum gain before the system reaches instability. See for instance this case here, when k is greater than 0 but is smaller than 8, there are no sign changes, the system is stable. When k is exactly 8, we have a row of zeros, the poles are on the imaginary axis, we have a marginally stable system. When k is greater than 8, this becomes a negative number and you have two sign changes, the system will be unstable. The Routh Hurwitz stability criterion is very useful and it's not very complicated, although it may seem a bit intimidating. However, in this lecture we have a bunch of exercises to cover this in more detail. I recommend you attempt these exercises on your own, and if you can't find the solution, then watch the videos that will be posted separately. Thank you.